not carrying enough oxygen. So here is the glomerulus. Now this is red over here, showing us that these are exposed capillary, if you will. However, on top of those we have a covering. This covering here is actually the inner layer of the Bowman's capsule. Here's the outer layer. We call this the parietal layer. Remember we had parietal and visceral? So this is the visceral layer of the glomerular capsule, which actually covers the capillaries of the glomerulus. There are special cells here called podocytes, and those podocytes actually, along with the fenestrated capillaries of the glomerulus, form the filtration membrane. So these are little podocytes, and they ripped them off here just so you can see the blood vessels underneath them. But this is the visceral layer of the Bowman's capsule. Here's the outer layer, then it comes over and covers the, and here's where the forming filtrate will be. This is where the capsule pressure, the opposing capsule pressure is experienced. In other words, there's fluid in here, and as we try to push more fluid in, it pushes back. For every action, there's an equal and opposite reaction. Basic physics. Here's where our filtrate now is entering our proximal convoluted tubule. Okay? If we come over here, we see our interlobular artery, our afferent arteriole. Here's my efferent arteriole coming out. Here's my glomerulus. Here's my Bowman's capsule. This is the proximal convoluted tubule, light green. We're going down here into the loop of Henle. And the dark green here is my distal convoluted tubule coming up here and it's dumping into a collecting duct. This is the portion of the distal convoluted tubule, which is right here, which is going to actually touch the afferent arteriole. We have it moved apart here. Interestingly enough, there are two kinds of nephrons. They're called cortical nephrons and juxtamedullary nephrons. The medulla is below this is the arcuate arteries and veins, so the medulla is down here. The cortical nephrons are either completely in the cortex or will just drop down a little bit into the medulla. Juxtamedullary nephrons have very big, long loops of Henle. Only about 15% of the nephrons are juxtamedullary nephrons, and their function is to keep the osmotic concentration of fluids in the medulla high. So we can actually see these things coming down here. Actually, these are extensions of the, if they're red, of the juxtamedullary nephrons. Okay. So here we see, in this particular presentation, the efferent arteriole coming out, forming the peritubular capillary bed. And so this is the peritubular capillaries. They're picking up stuff, and we can see they're dumping into, well, over here, they're dumping into the actually interlobular vein, coming into the arcuate vein. Now, there are blood vessels that go down into the medulla, and we're going to look at those right now in this model. Now, let's take a look at this model. We have one here. Oh, we got the other one over here I want to show you. Here, of course, is our arcuate arteries and veins. Here's my interlobular artery. Here's my afferent arteriole coming into a renal corpuscle, which is green here. Inside, we expect to find a glomerulus. Here's the efferent arteriole coming out. This is a total cortical nephron because, look, here is my afferent arteriole, my efferent arteriole forming a peritubular capillary bed. But coming out of my corpuscle over here, see this tan colored stuff, which is my proximal convoluted tubule, coming down here into my descending limb of the loop of Henle, ascending limb of the loop of Henle. Here is where the beginning of the DCT is touching the afferent arteriole. Here's my distal convoluted tubule dumping into the collecting duct. Again, this is where here and here is where we find the effect of antidiuretic hormone. This right here is a cortical nephron, a juxtamedullary nephron. Its loop of Henle is entirely down here in the medulla. We see extensions of the blood vessels coming down here These blood vessels here are called vasa recta, V-A-S-A, new word R-E-C-T-A, vasa recta. The vasa recta's function is to maintain the osmolality of the medulla at a particular portion. In other words, what's happening here, you'll learn in lecture, is that one limb of the loop of Henle is permeable to water, the other one is actively secreting sodium. So what we want to do, as water and sodium are pushed in here, we need to remove excess water and excess sodium to make sure we maintain the osmolality. So the function of the vasa recta, and these vessels here are also called vasa recta, part of this. The function of the entire vasa recta here is to absorb excess water and excess sodium to maintain the osmolality of that level of the medulla perfectly.